Welcome friends to EPG Pathshala and welcome to the paper of numerical methods in the subject of information technology. Today is our first module on the numerical methods, and so first we would have an idea about why do we need numerical methods at all, what are its importance, and what are the range of topics which we would be covering under numerical methods, what are their characteristics, how are they different from analytical methods, and then we will move on to some basic ideas about measurement of errors under numerical methods. See, when we have a scientific and engineering problem, even business problems, even statistics problem, even to economists. So, in the physical domain, when they encounter problems, they apply the principles involved of their subject and arrive at the mathematical formulation of the problem. And once that mathematical model, which is built upon those principles involved, is formulated to mathematical problem, then those mathematical problems are to be solved, and many times see those mathematical problems to be solved cannot be solved easily due to some or the other reason by analytical methods, and at that time we need numerical methods. The type of problems they are converted is, let us have some basic which we are going to cover in this our paper of numerical methods. See, the type of problems are not limited to the ones which I am mentioning now, but they definitely include, they are the basic things which one very commonly one encounters. Let us just have a glance at them one by one. See, the first one is about when problem is formulated, one is interested in knowing the root of an equation f x equal to 0. See, you are looking at the slide, see the graph is y equal to f x. See, when you plot the graph y equal to f x, the point at which it cuts the x axis is the root, because f x should be 0. So, one is interested in knowing the point x at which f x is equal to 0. You will ask is, can't we solve it by analytical method? See, the reason is quadratic equation, quadratic polynomial a x square plus b x plus c equal to 0, we know the root, each of us knows the root is given by x equal to minus b plus minus root b square minus 4 ac by 2a. But if we move to cubic or biquadratic, still they can be solved by analytical methods, but if we move to higher degree polynomial equations, no analytical method exists which gives us the root, or no such method exists by which applying which, or in terms of parameters of the polynomial, the coefficients involved, we can write down the solution of the root. And not only this, every time f x need not be polynomial also, they can be algebraic equation, they can be transcendental equation involving several ln function e raised to x sin x, like e raised to x sin x minus cos x equal to 0, and in those cases no such systematic analytical method is available to find root of those equations. So, here in case of numerical methods, we have different list of methods, iterative methods like the one you saw in the graph. See, we begin with the initial guess and we move on, we will be learning them in our subsequent modules. The methods, numerical methods are there by which we are able to find roots of an equation f x equal to 0. Similarly, there is another very important problem which is known as interpolation. You all are familiar with the interpolation, may not be knowing under the name of interpolation. See, many times, see, interpolation is known as reading between the lines of a table. See, many times, like if we know the value at 1, at 2 and we need the value at 1.5, many times we just take the average. So, interpolation is just knowing we have the values of some function at some points, and if we need the value at intermediate values, or we need to fit the function is not known to us, there may be readings at certain measurements at certain points of time or at certain ranges, and at that time we want to fit a curve to those data points. So, in interpolation we fit a curve which passes through those data points. If there are 5 data points, we fit a polynomial of degree 4. If there are n data points, we fit a polynomial of degree n minus 1, which is known as interpolating polynomial, which passes through all those points. So, in this slide you are looking the data points and the interpolating polynomial being fitted, which is passing through these points. The third particular case which arises is again for function approximation. The other method is which is known as least square curve fitting. As the name is, you have data points and you try to decide a fitting curve. Of course, the degree of the curve is decided beforehand. So, here the example, the graph shows you as a straight line is being fitted such that the criteria is that the error that is measured as the distance of the points from the straight line fitted, the sum of the square of the distances should be minimum, and that is why it is called least square. Sum of the square of the distances of the data points from the straight line is minimum, which is known as regression. So, this is the slide which is showing is a linear regression. So, to the data points using a model, a particular regression, it need not be always linear, it may be quadratic, any cubic spline. So, all the different methods of fitting a curve to the data points which best suits the data, and using that curve it is used for the prediction, maybe sales prediction, export prediction, or maybe population prediction. So, for all these, knowing the value of the function at unknown points where the nature of the function is not known to us, the curve equation is not known to us, there is either interpolation, regression, least square curve fitting, curve approximation, those techniques are used. Next, the case is like if we need the derivative of a function. See, either the function may be very complex, though you may be able to differentiate, but it may become a very complicated expression, or many times again we do not know what the function is. All we have is the value of function at the point that we have measured at different interval of time or at different domains or at different distances, and using that we want to estimate the derivative of the function. So, here again the method is we use a formula, we approximate again function by depending upon the order of the formula we employ. Here the example slide shows of approximating function by a straight line. So, at x 0 the y 0 is known, the actual curve is there, and at x the nearer point x 1 plus delta x, derivative is dy. In the approximation it is dy by dx. So, change in y upon change in x. So, it is measured as the vertical delta y upon delta x. This is how approximate value of derivative, one of the formula it is for calculating approximate value of derivative. So, what we have seen is like for finding root of an equation, for fitting a polynomial, for interpolation, for curve fitting, for regression, for numerical differentiation, and now comes a very important concept of numerical integration. You are familiar with the integration, but again see many times the integral function is integrable, we know it, but the integrand is not known to us. A very simple example is integral of e raised to x square dx. So, e raised to x square is the integral function, but we do not know the function whose derivative is e raised to x square. So, in general a to b e raised to x square dx we do not know. All we can do is write an infinite series for e raised to x square and use that the each term by term integrate, but that becomes computationally very time consuming and costly. Rather than that, and see secondly, it may happen again that the function is not known to us, all we have is the value of function at the points. And you know the integral, like suppose the velocity may have been measured at certain points and we want to know the distance travelled by the vehicle. And in that case, or it may be, see even a simple example is like suppose you have a lawn, because you know integral is nothing but integral of f x a to b dx is nothing but the area under the curve y equal to f x from x equal to a to x equal to b, the area between under the curve between x axis and under the curve. So, as a result, see when we let us say a very simple example of a lawn, if you have a lawn of irregular shape, you want to know how much mud to be purchased and you have a thickness. So, you want to, if you calculate the area, you can calculate the volume of the mud and you can know how many bags to be purchased. So, you need to have a value of the integral area under the curve, that means you need to have the value of the integral. So, here again because you can measure the value of the function and you see you are looking at numerical, this is a example where trapezoidal rule is strips are area is divided and numerical integral is used using data point function values at the data points, the integral is estimated. This is again the same, the more number of strips are there, and this is like a lawn example where you have measured the length of the lawn at several points, and using that length in terms of the value of the length, the area of this lawn can be calculated, which can be used to calculate the amount of mud needs to be purchased to fill the lawn with a particular height of the mud. So, these are very simple examples where we need them. Then we have solution simultaneous linear equations whose solutions we need. So, you know the simultaneous linear equation solution means a common point for both the equations. So, graphically it is the intersection point. So, here again of course, two variables you know you have the methods, but like say the same concept is extended to any number of variables, 3 variables, 4 variables, and again there the numerical methods are more easy to apply, less time consumingly, and they are very cost effective, and you can get the root to correct desired accuracy. So, these are some of the areas, not all, where the numerical methods can be applied to get the solution of the mathematical problem arrived at using the mathematical modeling of the scientific and different engineering problems. Similarly, there is one more example, solution of differential equation, because when we frame a problem and we apply it, we many times come across a differential equation whose solution we are interested, and again the numerical methods come to our rescue of finding solution of the differential equation. Again there are many methods. So, we have got the idea why do we need the numerical methods. The first one is that analytical methods may not exist at all to solve those problems. Second, analytical methods may exist, but then they may be quite time consuming, very laborious to apply, and maybe the huge data is involved and may not be easily computable. So, if the data is also large, because the numerical methods can be applied, can be implemented on computers, we will see in our just now that because they deal with the numerals, they deal with the numbers, right, they are very easy applicability to computers, and that is why using numerical methods we can arrive at the answers in a very fast way. And that is the reason why you see the weather predictions nowadays, mathematical model being built, simulation being done using computers, we are able to get quite good weather predictions now. So, now with this idea about why do we need numerical methods, now let us come to what characteristics these numerical methods possess. How are they different from the analytical methods? See, the first one is that in the case of numerical methods, we solve a problem which is numeric. What does that mean? What does that mean? Just take the example of quadratic equation ax square plus bx plus c equal to 0. This has parameters a, b and c. Using analytical method we are able to solve, we know a, b, c are constants and get the answer x equal to minus b plus minus root b square minus 4ac by 2a in terms of a and b. Similarly, integral of a to b x dx, we know the integral is x square by 2 and the answer from a to b I can say is b square by 2 minus a square by 2. So, we can know the answer is given by this. But in case of numerical methods, we cannot get the answer to a problem involving general parameters. The problem should be, it should become a fixed problem. It has to be, it cannot have any parameters, it has to have numbers. Like if I want to solve a quadratic equation using numerical methods, the equation 2x square plus 3x plus 5 equal to 0 can be solved. Another equation 3x square plus 7x plus 9 can be solved, but ax square plus bx plus c equal to 0 cannot be solved. So, coefficients should have the values, they should be having numbers there. Integral, if it is e raised to x dx, a to b cannot be evaluated, 1 to 2 e raised to x dx can be evaluated. So, in the case of numerical methods, the problems have to be numeric problems. The second is, because they are numeric problems, you arrive at a answer which is numeric answer. So, just suppose let us take quadratic equation itself. I have to solve 5 quadratic equations with different coefficients. I have to make 5 attempts of the solutions. I have to solve different equation, each different equation I have to solve again and again, because what we get an answer is we get an answer to a specific problem. But of course, the methods are general. Methods are analytical methods have been arrived using analytical mathematics. Methods ensure that if we apply those methods, we will get an answer correct to what we call as desired accuracy. We will just understand the word accuracy little later. So, the methods are there, more than one methods are there to solve a particular kind of problem. Like if you are come to finding root of an equation, we in our coming modules are going to learn bisection method, method of false position, second method, Newton-Raphson method, successive approximation method. 5 we are going to learn, and there are many other methods which you are encouraged to learn through the literature. So, numerical methods becomes an art in science and is a science in arts. Why? Because that requires a skill to choose a proper method to be implemented depending upon the data of the problem, so that you can optimize your solution to the desired accuracy, and also you can optimize time wise. So, there are many methods to solve a particular problem. To choose which one, or many times you may be required to choose a hybrid also, one after the other, to have the maximum efficiency of the output results in the least optimal time. So, in the case of numerical methods, we have a numerical problem. We have to solve a numerical problem. We get numerical answer. There are several methods. They are logical methods. They have been arrived using analytical behind the screen. Analytical methods have been used to derive those numerical methods to be applied. Many of them are iterative. Some of them are even direct methods. The nature of iterative methods we will just see in the next slide. And because of they are numeric problems, they are converted to numeric problems, they can be very easily implemented on the computers. So, even the large data size problems, highly complex functions, those problems can be implemented on the computer very easily to get the desired answer. And these methods which are analytical, see, they ensure us that if they are applied properly, if the conditions are ensured, then in most of the cases we have an idea also, and we get that what is the upper bound of the error. So, we can get an answer to the desired accuracy. Let us come to the methods to be applied can be direct or iterative. What is the nature of iterative method? See, in the case of iterative method, the method is there, that is the process which is defined. We make an initial guess to the solution of the problem. Now, how to make this initial guess? As we come to the methods, we learn it, we learn how to make an initial guess. That also is a skill, because choice of initial guess many times plays very important role depending upon the data and the parameters involved. So, initial guess is made. So, initial estimate of the solution is made, that becomes input to the process. So, process, that is a method which is applied, and we get the output. Now, this output is closer, it is supposed to be better than the input. So, it is closer to the root. If you will check the output, if you are satisfied with the output, we will stop, we will exit with the answer. But if we are not satisfied, then this output is a better estimate of the solution. This will become input to the process, and again we get output from the process. So, this process continues. So, every time when we get output, we will check whether we have reached the desired accuracy or not, whether we are happy with the solution or not. If we are satisfied, we will exit with the solution. If not, that becomes again input. So, this is how the process is repetitive in nature. So, that is called iterative method, and that is why, because they are repetitive in nature, same formula, same method is to be applied again and again, all the more they become more suitable to be applied to computers. So, with this knowledge of the nature of numerical methods, the problems to which they can be applied, why are they needed. Now, let us come to the next aspect of today's topic, and that is the quantification of errors. See, because they are iterative nature and the mathematical modeling takes place, so there are different sources of errors and different types of errors. About different sources of error and different types of error, we would be covering this in our next module, but today let us learn how to quantify an error, how to measure an error. So, for that, see, the word, before we learn to quantify the error, let us first just understand these two words. The one word which is accuracy I was using previously, that we can get the answer correct to desired accuracy. So, what is meant by accuracy and what is meant by precision? See, accuracy means if we say the answer is more accurate, that means it is more closer to the actual solution, the true solution of the problem. So, closer the value, more accurate it is. So, that is how the accuracy is there. How close the result value is to true value, the closer the result to true value, more accurate it is. Whereas, precision means how close the values are there together. So, when we are getting successive approximate values, if they are very close, we say they are precise, they have more precision, they are getting closer and closer. But this precision getting closer and closer, is it getting closer to the actual true value or is drifting away to some other value? That becomes a question mark. So, precision does not ensure accuracy, but accuracy does not always ensure accuracy. So, this is just a slide which shows you have a timeline, your equation state line, the data points are quite near the line, right. So, they are accurate, but of course, the points are far. So, they are not close. So, they may not be called precise, but they are accurate. Whereas, this is an example where the data points are very close to each other. So, they are like precise, they are precise, but not accurate because they are far from the line which reflects actual true solution. So, with this understanding of the accuracy and precision, now let us come to the measurement of errors. So, how one very obvious is we have a true value and as our numerical method we have got a approximate answer to the solution of the problem. So, that is the approximate value, or it could be even measured. Let us say this hall where I am sitting has a length of 20 meters and I have measured it, its actual length is 20 meters, that is a true value, and by measurement I have measured it 20.1. So, that is my approximate value which I have arrived through my measurement. So, the error, what is the error? True error, E for error, T suffix for true. So, ET is true value minus approximate value, that is our true error. So, just for example, the true value of the quantity is 7.893 and approximate value is 7.672. Then the error, the true error is true value minus approximate value. So, true is 7.893, approximate is 7.672. So, 7.893 minus 7.672, it gives the answer 0.321. See, the true error can be positive or negative. If we have erred on the higher side, means our approximate value is more than the actual value, the true error will be negative, and if we erred on the negative side, means if our approximate value is less than the actual value, the true error will be positive. So, if the true value is 7.893, but the approximate value is 7.975 higher than the actual, then the ET is 7.893 minus 7.975, it gives the answer minus 0.082. See, usually we are not interested in the sign of the error, positive or negative, but we are more concerned with the magnitude of the error, how far it is, what is the distance, how far from the actual value our approximate value lies. So, distance between approximate value and the true value. So, we are interested in the magnitude of the error, not in the sign of the whether positive or negative, and that is why the word absolute error comes in. Absolute error or absolute true error we may call it right now. So, is given by absolute value of ET, that is absolute value of true value minus approximate value. See, usually if we have to have an idea, the absolute error does the job, but many times depending upon the case, absolute error may not be a good measure and one may need to normalize the error. See, the reason is error, this error, absolute error, question is in how much. For example, again I come back to the example of my room length. See, if the length is 20 meters and I measure it as 20 meters and 1 centimeter. So, error is of 1 centimeter in 20 meters. Let us say the other problem. Suppose I have a ball pen. I want to measure the diameter of the ball pen's refill. Let us say the diameter is 1 centimeter. I use vernier caliper and the diameter of the refill comes out to be, I have measured, I have done some blunder and I have measured, instead of 1 centimeter, I have measured it 2 centimeters. Again the error is 1 centimeter. Earlier also the error is 1 centimeter, now also the error is 1 centimeter. So, absolute error is 1 centimeter in both the cases. But which measurement is more erroneous? Obviously, error of 1 centimeter in 20 meters is, each one of us will agree it is acceptable, but in the case of refill measurement, I have done 100% error. Instead of 1 centimeter, I measure it 2 centimeter, 1 centimeter extra, it is almost 100% error. So, this is very important, what is our acceptable tolerance limit of the error, and that is why if we have an idea about the range of the values of the solution, one may work with the absolute value and one many times works, but then if we have no idea, relative error is needed, and relative error is nothing but given by absolute error or the error divided by the true value. So, it is true value minus approximate value upon true value, that gives the real field of the amount of error committed, and this is known as relative error. So, and if you multiply this relative error by 100, that gives the error percentage error. So, percentage error of absolute percentage error is true error divided by true value into 100. Let us take the same example which I cited and calculate the relative error in both the cases. So, earlier case relative error, see 20 meters, error is 1 centimeter and true value is 20 meters, that is 2000 centimeters. So, 1 by 2000, so it is 0.0005 is the relative error and that gives 0.05%. So, it is very less, 0.05%. Whereas, in case of our example of the refill of the ball pen, error is 1 centimeter, actual is 1 centimeter. So, it is relative error is 1 by 1 and multiply by 100. So, it gives you 100% error. So, obviously, 0.05% is too low, very acceptable, happily acceptable, but 100% is highly unacceptable, though the absolute error is 1 centimeter in both the cases. So, many times one needs to work with the relative error. A very concrete example is like when you are finding some constant, like let us take the example of elasticity constant of a metals, Young's modulus. So, they the constant are of the order of 10 raised to minus 8, 10 raised to minus 9 or 10 raised to minus 12. See, in that case you have no, if you have no idea about what order it is, then so many point zeros are coming. So, if the error is a 0.001 absolute error, that will be highly unacceptable, but then in that case if one is interested in answer correct to certain number of significant digits, the relative error plays a nice role. One can use the relative error concept to find the answer to desired accuracy. See, now question which you may ask is a very natural question. We have given the expression of the approximate error, relative error, percentage error, and in those expressions we are using true value. If we know true value, why shall we find the error? What is the need of the finding error if we know the true value? So, see, of course, that expression may be useful, like suppose we are testing a program output, or let us say we are using heuristic in our AI problems, and in those cases we want to test the program for many instances. So, that is like we are doing the supervised learning of a problem, and those cases we are checking the program where we know the answers, so we know the true values and we are calculating the errors. So, those cases the true value and those expressions which we have learned are useful, but in those methods, in those, like if we are finding root of an equation and I do not know the true value. So, in those cases how to work with those formulas. So, there this true value we replace by the approximate value. So, our formulas change if the method is iterative. The most recent estimate is taken as the true value and the previous estimate is taken as the approximate value. So, what we get is absolute value of approximate error as the current estimate minus previous estimate. So, current estimate is like true value and the previous estimate is like the approximate value. And similarly, the other terms, approximate relative error will become absolute, numerator will become absolute approximate error and divided by the current estimate. And in order to calculate relative error, that the approximate percent relative error we may call it, will multiply the approximate relative error into 100, which will give us approximate percent relative error. And this approximate percent relative error will denote by small e and suffix a for approximate. So, absolute value of E. Usually in our iterative methods to follow in our coming modules, when we learn these different methods which are iterative in nature, we are going to use either the formula of absolute approximate error, that is the current estimate minus the previous estimate, to be less than some pre-assigned tolerance limit to stop, to exit, to decide whether we have reached the desired accuracy, or we will use the concept of the approximate relative error to see that we have reached the desired accuracy. Just this table, just to illustrate you, this table, if you are looking at, is a table which we would be getting when we learn a bisection method to find the roots of an equation. Just focus on the columns of Ck. See, these Ck columns are the estimates in the different subsequent iteration. So, first iteration we have got the value 0.5 is the estimate, second iteration 0.75 is the estimate, and so on. So, if we calculate relative error, the right side I have calculated relative errors. See, first after the first iteration, see 0.75 becomes the current value, 0.5 of the previous iteration, that is the approximate value. So, the numerator is the approximate error 0.75 minus 0.5 divided by the true value role is taken by the current estimate, it is 0.75. So, 0.25 upon 0.75 is 1 upon 3 into 100. So, relative error, percentage relative error approximate is 33% after the first. Again the next iteration, the current estimate is 0.625, be focused on the Ck column. So, the third row 0.625 is the current estimate, the previous estimate is 0.75. So, the ratio is approximate error 0.625 minus 0.75 divided by the current estimate 0.625, and this into 100 gives you 20% error. And this is how the method goes on. Each time if you want, you can check the relative error and come to the last 3 rows. So, last but one row and the previous row. So, we have current estimate, the last but one iteration 0.68227 minus 0.68239 and divided by the current 0.68227, and that gives 0.01758%, and the last one 0.68233 minus 0.68227 similarly divided by 0.68233, it gives you 0.00879 percent relative error. And if you are looking at the last column, see function values, they have become almost 0. So, we have got the root of the equation. So, this is how the concept of approximate error and the approximate relative error can be taken to have a stopping criteria about the relative error. Now, see, if we want the answer to desired accuracy, as I said, we can take epsilon a to be less than epsilon, and many times we are interested in the answer correct to certain number of significant digits. So, in that case the error should be less than, absolute value of E a should be less than half into 10 raised to 2 minus m, where we know that we need the answer correct to m significant digits. Now, this formula is due to Scarborough. What is significant digit means and what does this mean, we will discuss at length in our next lecture. So, as far as today is concerned, what we have learned is what is the importance of numerical methods, why do we need them, why numerical methods play important role in today's scientific and engineering problems, and for computer scientists, economists, mathematicians, statistics, all business problems, how do the numerical methods play very important role there, what are their characteristics, how they are to be applied, how do they play important role, and also we got an idea about the errors that is the measurement of the errors, in fact, approximate error, relative error, absolute error. And when we meet next, we will discuss on different sources of the error. See, when we solve, we apply a numerical method. Some errors creep in before the mathematical formulation when the formula arrives at. So, what are the different stages where the errors come in, and what are the different errors when we apply numerical methods to a problem in during the calculation, during the application of the method come in, and how can they best be controlled to give us the optimal solution. So, bye till then, thank you, and once again thank you very much for visiting APG Pathshala.